Good afternoon. So last time we were talking about airfoil data. Today I want to talk about this 0009 airfoil. It's an NACA 0009 wing section. And there are two plots for each airfoil in the back of the book in the appendix. One is CL versus alpha in degrees. So make sure you notice the units. And then the other is CM. If you look real close on this, this is CM over C4. So this is the moment about the quarter chord point. Plotted versus angle of attack. And the key thing to notice, well, one of the key things is that the axis numbers labels here are for lift. And these numbers here are for the pitching moment. It's real tempting and easy to read off a pitching moment value and come over here and read minus 0.85, but you have to look at the numbers in this column here instead. So this is lift versus angle of attack. This is pitching moment. And the reason there's several plots is that a bunch of these symbols correspond to different Reynolds numbers. And then the top set here are with a flap deflected. So this is no flap with a flap deflected, and then the symbols correspond to Reynolds numbers. So for a minute, I'm going to switch to the board. We're going to draw the key shapes that you see here. Most of this plot is a straight line. So unless you're in the region where it hooks over at the bottom or the top, we can just use the equation of a line to predict this as well. So I want to go through that. So here's what, in general, one of those plots looks like. We have angle of attack in degrees. And I'm going to draw this general. The plots we were looking at, this intersection point here is at the bottom of the axis, is at 0 lift. But in general, this intersection won't necessarily be right here. And this point is called CL alpha equals 0 because here the angle of attack is 0. And then this goes up in degrees. And then this point here is called the angle of attack when the lift is 0. So in mathematical terms, this is the y-intercept, and this is the x-intercept of our line. Because it's a line, we'll also talk about the slope. And in this book, they label it A0. It's the derivative of CL with respect to alpha. And it's called the lift curve because this is the lift curve slope. This region up here where it hooks over is when we get that stall. Remember with the boundary layer, we talked about how if you get at high angles of attack, the pressure recovery causes the flow to go backward. And if that happens enough, that boundary layer detaches and you get a stalled wing. So this whole region here is stalled. But in here, all of the airfoils have pretty much linear behavior, straight line. So in this region, we can write equations that predict we can either do it in terms of the x-intercept here, So really this is just saying, okay, I'm measuring the distance from this point over to wherever alpha is, and I'm just taking the slope up from that, the slope up from 0. Or I can write the equation in terms of the y-intercept, where we say the lift is the lift at that intercept. Oh, this should be lowercase l, because we're talking about an airfoil. So it's that y-intercept plus the extra rise up with the slope after that. And since that's the y-intercept, alpha starts at 0, and you just go up from 0 to wherever the alpha is. So these are just two different forms of the equation of a line, right? This is y equals mx plus b, and this is in terms of the x-intercept. Now for airfoil problems, we typically don't use these equations. We just look it up on the chart in the back of the book, on the graph. Now when we get to 3D wings, we do use these kind of a similar type of equation, because for the 3D wing, we don't have a plot for the wing. All we have is the airfoil, and then we'll have to do some extra calculations to get the equations that we will predict the lift with. All right, since we're talking a little bit about separation and stall, your book has a couple figures that I copied. So this is figure 5.9. I think that's in an older edition. But if you look closely, and this is a little bit fuzzy, the streamlines, what they did was they put oil dye on the wing in a wind tunnel. And you can see that there's a nice smooth flow. The oil streaked back in a nice even manner. So this is completely unstalled. And this is at the beginning of stall. We get nice, smooth streamlines till you get to the lower backward, the aft portion of the wing. And that's where that separation starts to happen. And you can see this swirled flow here from that stalled region. And then if you increase the angle of attack even more, if you look carefully at this, you can see that there's no streamlines going straight forward and back along the wing. It's all just swirled around, and the flow is completely messed up over the wing. And so that's why you lose lift during that stalled region. Okay, so next I want to talk about how you read the Reynolds numbers on these plots. So remember we talked about how this curve has circles and squares and diamonds, and then this one has upside down triangles. So on the next plot, this is the drag polar, so it's CD. You'd think it's CD versus alpha, but they plot this as CD versus CL, because it turns out that's a better way to plot this. So the lift coefficient is down here. Pitching moment is here, but the one we really want is drag versus CL. And these curves look like parabolas. And the different symbols tell you which graph you need to look at. And you go down to the legend, and it's per Reynolds number. So the R here is Reynolds number. And this is 3 times 10 to the 6th. So Reynolds numbers tend to be on the order of millions, 10 to the 6th. So the circles are 3 times 10 to the 6th. Squares are 6. Diamonds are 9. Triangles, right side up, are 6. Notice standard roughness. So they're saying these up here are for smooth airfoils. This is a standard roughness for an airfoil. And then these two down here are for a simulated split flap. I'll show you a picture at the top. So upside down triangles are for a split flap. So if there's no flap deflected, you use the top ones. If there is a flap, you use the bottom two. And the picture of the flap is up here. It's this thing down like that. So for the flap not deflected, it's backward. For the flap deflected, this thing is pointed down. And if you look at this, this changes the airflow because the flow is going to hit this flap and have to go around this way. So you get more pressure on the bottom of the wing. And that's why in this plot, the flaps give you a lot more lift coefficient vertically than the unflapped airfoil. So we'll do an example here in a minute. We'll calculate Reynolds number, figure out which symbol to use, and then look at the plots to pick off numbers. The other thing I want to point out before we switch away from this graph is if you look at the pitching moment, it's constant with angle of attack. In fact, it's 0 because this is a symmetrical airfoil. We talked about how if you take the pitching moment about the quarter chord point, pitching moment does not change with angle of attack, and so this is experimental evidence that that really is true. So CM does not change with angle of attack about the quarter chord point. All right, so next we're going to set up our example. So key features that I talked about, the symbols, have to do with Reynolds number and flap deflection. So you have to find the right symbol. The pitching moment about the quarter chord point really is constant. With angle of attack change. And we need to talk a little bit about the definition of lift coefficient for an airfoil, because we defined CL as the total lift divided by the area times Q infinity. But if we have an airfoil, it has an infinite length. It's called an infinite wing. So what's its area? Chord times infinity is going to give an S of infinity. That makes no sense. So that's useless. So what we do is we do this per unit area. So we just put 1 in for the length. So what that means is you get lift per unit length. So if you're working problems for an airfoil and you need to calculate an area S, you just take the chord and multiply by 1, and that gives you the area. So it's lift per unit span. All right, next, let's do the example. So we have an NACA 0009. So it's a 0009. This is the appendix data that we have. So it's Appendix D. So we go back, and those are the 2 pages I've been showing you. And so they're saying they tested an infinite wing in a wind tunnel. So they put it all the way to the walls of the wind tunnel, so there's no flow around the tips of the wing. So it's an infinite, effectively an infinite wing. And it's flying, the wind tunnel was going at 50 meters per second. So that's the velocity. The chord, this is how big the airfoil was, 1.3 meters. And the angle of attack is 4 degrees. From the charts, if we do this wind tunnel test and we want to compare our numbers to what people have gotten before, we look at Appendix D and we get CL, CM, and CD. So really this is an example of how do you look up data on these charts and plots. We're going to do a test of your vision. If you have a textbook, you're going to come out way ahead because I'm going to put the plots up on the screen and you're going to read data for me for CL, CM, and CD and write them down on your notes. So here's the CL plot. I need to get it set so that you can read the correct angle of attack. So you're going to read at an angle of attack of 4, go up and pick off CL and CM. So do that right now. Again, if you have your book, you can pull your book out. Otherwise, squint at your screen or get close to one of the projector screens. Good deal. Everybody should be doing this because you're going to be doing this in homework, so this is your practice. You have 39 seconds to get CL and CM. You always need a time limit, right? If you watch football, the play clock is set to 39 seconds. Basketball, the shot clock. If you watch tennis, there's a clock that tells you how fast you have to serve the ball. I don't know soccer that well. Is there a clock there or you just play? All right, let's do the easy one first. What are you getting for CM? Somebody shout out what you get. So, shout it out. And which one are you reading from? Yeah, so you need to ask me a question now. What question do you need to ask? Is what? Well, that's important. We're going to need that. But all of these look the same, right? What's the difference between the 2 series of plots? Flap, right? So you need to say, is a flap deflected, right? Because I didn't tell you that. So no flap. Pretty much if you aren't told there's a flap and what the deflection is, you're going to have to assume no flap. So does that change your answer? What do you get now? Yeah, that sounds good to me. Everybody else, you guys getting 0? Where are we reading this? We're reading this from the plot that goes across. These are lift curves. I'm asking for CM. So you look here and pretty much you read all the way across, you get, oh, don't look at that 0, look at this 0 over here, right? How about CL? Somebody brave enough to shout out a number? .4. How's that sound to you guys? Are you good with that? Turn around and look at the screen. Do you like the number for CL? How about you guys here? We're looking for CL at 4 degrees. That's why I'm going through this. You need to ask questions if you don't know what's going on. 4 degrees. So 4 degrees. It's right here, right? So you go up, and where are we? Oh, that's CM. We're up here, right? I even got an arrow. Where are we at? 0.4? Is that as good as we can get? Good point, because we haven't calculated Reynolds number yet, right? So how close can you get right now? 0.4. Your boss comes in and says, give me a CL value for this airfoil. Here's the chart. What are you going to say? I'm guessing then an answer of I don't know is not correct. Unless you say, I don't know till I calculate my Reynolds number. And then he'll go, whoa. So I'm going to zoom in further. Can you get me a better answer? This line's 0.4, this line's 0.5. So we could probably get right in here, couldn't we? So what was that? It'd be about 0.43 maybe. And if you're smart, you'll say this is 0.43 plus or minus about 0.015, right? That's about as accurate as we could read it. It's experimental data, so your boss will want to know, well, how good is this number? Should I count on it to be 0.43? If it's 0.44, will my airplane crash? Hopefully not. So that's how you read this. So, but now let's especially notice that all of these symbols are pretty much right on top of each other. So we don't so much need Reynolds number for this, but how about the drag? We've got to take that CL number that we just read, read it off the bottom here, and go up. So what drag value do we get? So this is the line we're on here. Let me mark it so that we can keep track of it. 0.43. So we are along a line right here. And now you definitely would say, I don't know, because I don't know whether I should read circles, squares, triangles, green hearts, or pink diamonds, right? So let's calculate Reynolds number. And it's the Reynolds number for the whole length, so it's, you put this chord in here. So you guys calculate this. What do we need to know? We know the velocity, we know the chord. We need the density in mu, right? So we need additional information. Sea level, standard atmosphere. We need to ask, well, where are we flying? So sea level, standard atmosphere. Density is 1.225. kilograms per meter to the third. And you're going to have to look up mu. You guys probably don't have that memorized. I don't. So go ahead and pull out your calculator, your phone, or pull up the calculator on your PC in front of you, and let's calculate Reynolds number. What'd you get? 4 point what? 4.45 times 10 to the 6, so it's millions. So that looks like it's in the right range of what we were seeing on the chart, right? Anybody else get this number? Good? All right, we all agree. So now we got to go back to the, oh, I need to put this on the screen for the Zoomers. So there's a Reynolds number calculation. And now we got to go back to the chart for the drag, and we're going to read off our CD value. So I'll give you a minute to get caught up here, and then I'm going to switch back to the chart. Okay, back to the chart. So we have 4.5 million. We go, gee, we don't have that. We got 3 and we got 6. So it's kind of halfway in between, so we can do a visual interpolation. It's going to be between the circles and the squares. So we read up at our CL value of 0.43. Circles are here. Squares are here. So we get a number about something. What's our axis? This one's kind of tricky. So this line is 004. This is 008, so you have to count 004, 005. So this is 006 is that line. Go across. This is 007 up at the next line, so this is 006.2 maybe. So you're going to have to do this mentally every time you read off of here. I have to, or otherwise I'll get messed up. You have to essentially mark the lines in between and then know how much of an increment you've got going between this line and this line. So I read about 0.0062. Now if I wrote, I said, I'm looking at this chart and I write, I'm reading my drag as 00623971. What do you say? Yeah, you say I made up those last numbers, right? Because there's no way. In fact, we're probably accurate to 0.0062 to plus or minus 0.00001 maybe, or 0.00005, depending on how confident you are that you can pick the number. Now what you can do is take your book and go to a copier, or take your phone and zoom in on that region and get a little bit more accurate value. But eventually you'll get to the point where the width of the line, you just can't read past that accuracy. All right, so there's the value we chose. So now if we wanted to calculate the total lift, the total drag, and the total pitching moment, we have to use the definition of CL, CM, and CD. So we're going to need to take CL, multiply it by S, and multiply it by Q infinity. And then to get the drag, let's do the pitching moment. The total pitching moment is going to be CM times S times Q infinity times the chord. Remember that it got divided by that. And then the drag is CD, S, Q infinity. So we need to calculate Q infinity. So I'm going to do that over here. Now we have to remember the definition of dynamic pressure. That's why it was on the quiz and why we spent a lot of time talking about it. Remember, it's this term that showed up in Bernoulli's equation. So that's why we gave it a name, because it shows up in that equation all the time. And our speed was 50, right? And we've done the units on this enough that you find out that a kilogram meter per second squared comes out of this. So that gives you newtons, and then you get a meter squared on the bottom to get newtons per meter squared. So there's our dynamic pressure. Now we need to calculate the area, because I'm going to need that number over here. And the chord is 1.3 meters. And it's an infinite wing, so we put in infinity. No, we don't. We do it per unit span. So the area per unit span is 1.3 meters squared. So then we can directly go in here. That one's easy. We get 0. If you punch these out, by the way, we were reading numbers off of here, and we didn't put any units for CL, CM, and CD. Why is that? Is that a mistake? Yeah, those are unitless. Remember, we took newtons per meter newtons and divided by the area and the dynamic pressure. So we get unitless. We're taking pressure units divided by pressure units. But we get units out of here because we multiply by meters squared, and then this is newtons per meter squared, so we get newtons out of that. So it looks like we got about 10 minutes left, maybe a little bit more. So all of this is for airfoil, two-dimensional, infinite wings. And this is how you do those. You find the data for it in your wind tunnel data, and these are how you do the calculations. So that tells you how to do a lot of the problems on the homework that you're working on right now. I think all of that is airfoil data stuff. And that's been assigned now. It's due. So I think we go over it on Monday, and then we do a quiz and turn it in on Wednesday. It's on Blackboard. It's all this airfoil data stuff. How about a finite wing? So what are we going to do? Because we can't build an infinite wing. So we have to correct the lift for the fact that we get that flow over the wingtips. So some of the terminology we need to start talking about for that. Because it comes down to how long and thin the wing is. If it's almost infinitely long, the airfoil data is going to be pretty good. Whereas if it's a real short, stubby wing, then you get a lot of flow around the wingtips, and that flow covers most of the wing because the wing's real short. So the parameter that measures how long and thin a wing is something called the aspect ratio. So infinite wings have two-dimensional flow, meaning there's no flow along the span or around the wingtips because there are no wingtips. Whereas finite wings have three-dimensional flow, including wingtip flow. So if you look at a wing, like that, it's going to have a wing span, and that's just the tip-to-tip length of the wing. And I deliberately drew it with a non-uniform chord. The chord changes depending on where you are. So the chord is a function of the x distance out along the wing. And the wing will have some kind of area that we'll have to figure out. In fact, we'll have to integrate that chord times the position we'll get little area strips and add them all up. But we'll eventually be able to calculate the wing area. And depending on the shape of the wing, that's either easy or hard. In a minute, we'll look at rectangular wings. Where you simply multiply the chord times the span because the chord is constant. Or if we had a triangular wing, we all know how to calculate the area of a triangle, right? 1/2 the base times the height. But if it's some tapering, if the wing tapers, that is the wing tip is lower chord than the wing root, or we get something goofy like what I'd shown, you have to integrate this area to get the value. All right, so the number that's important, that's a measure of how long and thin the wing is this really cool symbol that I like to draw. It's a combination of an A and an R. Now in most books they can't typeset that, so they'll write it as AR. But have some fun practicing writing that letter. And it's called AR because it's called the aspect ratio. And it's just a measure of how long the wing is compared to the area. So you take b squared, the length, divided by the area. In a minute, the examples I'm going to put up here, you can see why this is an important measure and how it works. Because we're going to do some real easy rectangular wings. So the first one we're going to do is a square wing. So they're both 1 meter. So the wing area is going to be C times B, because it's a rectangle. It's going to be 1 times 1. And the aspect ratio then is going to be B squared over S. So it's 1 meter squared divided by 1 meter squared. So the aspect ratio is 1. Surprise, right? So a low aspect ratio means not a very long, thin wing. So let's do a long, thin rectangle. I'm going to draw this to scale so that you can see what an aspect ratio of like this looks like. So the chord is 1 eraser. And then the span is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 erasers. So we're over here. So the wingspan is 10, and what are the units? Erasers. And the chord is 1E. Don't confuse E here with the charge of an electron, because we're not doing physics. Well, we're doing physics, we're not doing electromagnetics. So does that look like it's pretty long and thin? Kind of looks like almost a 2x4, right? Okay, so let's calculate the aspect ratio for that. So the wing area is still a rectangle. So it's 10 erasers squared. And then the aspect ratio is going to be B, which is 10 erasers squared divided by 10 erasers squared. So 10 squared is 100 divided by 10. So this thing has an aspect ratio of 10. So an aspect ratio of 10 is pretty much long and thin. You're in senior design, and you're doing aerodynamics. And you go to your structures guy, and we'll find out that how efficient the wing is directly related to the aspect ratio. The longer and thinner it is, the more efficient the wing can be. You go to your structures guy who has to build this thing, and you go, I want to build a wing that has an aspect ratio of 100 because it gives me the best lift. What do you think about that? It doesn't look like we could actually do that, right? Imagine this, we're talking, if it has an aspect ratio of 100, one eraser here, we've got to take this and go 10 times more. So imagine a structure that's going to be able to support that thing being that long and thin. Pretty much anything over an aspect ratio of about 10 or 20 is pushing the structure limits. Some gliders will have a higher aspect ratio of like maybe 40. And they're having to use advanced composite, carbon reinforced epoxy, other kinds of materials to get that load carried over that long, thin wing. We're about out of time, and that covers pretty much everything I wanted to do today. So let's see, next lecture will be about something called the pressure coefficient. The definition's in the book. If you want to work ahead on the very last problem on the homework, you can. It's an easy, you just plug and crank into the pressure coefficient formula. And then after that, we'll talk about, well, how do you predict the lift, drag, and pitching moment of a finite wing so that we can build an airplane. And all of this is leading, of course, to your career in aerospace engineering, but also your follow-on classes to this. But before Thanksgiving gets too close, a couple weeks before, you'll get a design project where you are to design and build a glider virtually inside X-Plane. So I'll show you how to use the flight simulation program X-Plane. And a part of it's called Plane Maker, where you actually give it the geometry and the specifics of your airplane, and then that's what you fly. So you can virtually build an airplane and fly it in X-Plane. It's pretty cool. We'll divide up into teams where people will be working together on this project, and then you'll demo your airplane, your glider. So in that, you'll need to build a finite wing, and there will be calculations in the scoring of that based on the weight, because if you build your wing too long and thin, then the weight goes up because you have to have the structure to support that. So we'll get into, give you some more tools about how to do that and how to design your wing for that. All right, questions or comments about the semester? We're about halfway through. How's it going? Are you in barely surviving mode or doing okay mode? Thriving? I don't know if anybody's thriving in all this, but you wouldn't say thriving, yeah. All right, that's it for today. Keep rooting for the people that are developing vaccines.